All right, go for it.
Okay. It is my pleasure to introduce Professor Ron Cohen from the Chemistry of Earth and Planetary Sciences at UC Berkeley. Ron has a really nice quote that I'm gonna, in his bio, atmospheric chemistry, a chemical perspective on the effects of human activity on the Earth's atmosphere, on exchanges between the atmosphere and the biosphere. So there's what atmospheric chemistry is, and that's what he's going to talk about today. Anyway, Ron got his PhD at the University of Berkeley in 1991. He was a postdoctoral fellow and research associate at Harvard under James Anderson, and that's when I met him. It was in Fairbanks, Alaska in 1997 on a field campaign looking at stratospheric ozone. And I will say that Ron pulled me aside and taught me enough chemistry so I wouldn't sound like a total idiot. And he was the first person that did that, so I appreciate that. Anyway, joined as a faculty at Berkeley in '95. He's also a faculty scientist for the DOE Lawrence Berkeley Livermore Laboratory, and was a visiting professor at the Max Planck Institute for Chemistry. What he's going to talk about today is mapping urban air with neighborhood resolution, and in particular about his Berkeley Environment, Air Quality, and CO Network, BECA. So, welcome Ron.
Thank you so much, Brad, and thank you to the rest of you who I've had a chance to talk with and meet with today. It's really a pleasure to get a chance to be here, to meet some grad students, to check in with old friends. Both Brad and Matt are people who I met and worked with in Fairbanks and other places thinking about the stratosphere. Tim was my grad student. Gil I know before all of them. Gil was a postdoc when I was a first-year grad student, and he was always someone we looked to for advice. So I want to tell you today, come in. Okay, you can go that way too. I want to tell you about a project, and it's one where we've been really thinking about, often in atmospheric and earth sciences, what we try and do is make exquisitely beautiful measurements in one location and then extrapolate to the world, or to exaggerate. A friend of mine says we make one isotope ratio measurement in a meteorite and say something about the origin of the universe. I want to take the opposite approach today. I want to think about what we can do if we make lots of medium quality measurements and generate a map to get much more information in space and not spend all our intellectual energy figuring out the extrapolation. And we're looking for that compromise between exquisitely beautiful measurements and lots of distributed measurements. And I'll give you our take on what's a good compromise, but I hope I leave you thinking about, there might be other good choices to make. And it starts with, we started this project thinking about the shape of cities, and we do a lot of satellite remote sensing, and most of the time if you're thinking about satellite remote sensing, at least 3 years ago, the way you were thinking about it is you were thinking about the city as one large area source, and you weren't worried about the structure inside the city. And we wanted to do this project to sort of, in the way that microscopists in chemistry think about small-scale structures and variability in small-scale structures, say inside one of your cells. Let's think about cities in that same way. How can we get inside, into the near field in the city where the structure of the city matters? And you see here an example of that. This is downtown San Francisco. If you've been to AGU before we started traveling the country for AGU, it was always down here on the other side of these tall buildings. But you can see just in this image that the city has structure, that it's different where all those tall buildings are than a few blocks away. And we might imagine that the emissions into the atmosphere vary on those spatial scales. So that's what we set out to think about and to build an instrument that would characterize. To step back, the questions that drive that research and the rest of the work in our group are really, how is climate interacting with atmospheric chemistry now, how will it in the future, and then how can we make the air safer for people to breathe. And I'll just remind you that we've done an extraordinary job of this. I grew up in New York City. This image over here is summertime in New York City, what it typically looked like when I was a kid. You can't really see the George Washington Bridge there over the Hudson River, and more often than not, that's what it looks like today. So that's one of the things that we've done by controlling air pollution, and lots of places in the world have made that transition. So I will get a chance to talk about the variety of kinds of work we do in our group today, but we do some of each of these things. We've made over the years lots of measurements at the surface from towers like this one over a forest. We used to fly quite regularly on the NASA DC-8 aircraft, thinking about distributions of nitrogen oxides, both at the surface and over long distances in the mid-troposphere. We're still deeply involved in using remote sensing of NO2 for various kinds of projects. And I'll talk to you today about sort of the intersection here, where we make lots and lots of measurements of chemicals, and we do some sort of connection to a model of the atmosphere as we try and interpret what those observations mean. So here's an aerial view of the San Francisco Bay Area. Berkeley is over there, city of San Francisco here. This is a 10-kilometer across that peninsula, just for scale. Silicon Valley and all the tech companies down there. And let me go back for a second. What I want you to think about are the many different ways that maps, here's one kind of a map. We're going to try and talk about mapping the air. You know, how do we use maps? How do they teach us something about the atmosphere? So here's a map from space. This is a map generated of the column of NO2 over North America. In this case, the map is summertime in 2005, 2006. And you see the average column of NO2 in the troposphere. You see Chicago, the eastern seaboard cities, Los Angeles, San Francisco. This is 2 500-megawatt coal-fired power plants. And so that's what you see when you look at NO2, big cities and power plants. You see that we controlled the emissions over the 7 years following that previous image in a dramatic way. Emissions went down by about 7% per year over this period of nitrogen oxides. They went down, if you followed that record, you would find the day at the power plants where they introduced controls. Power plants went offline, the emissions were zero. They put controls in the stacks, and then the emissions were much lower. In the cities, it happened more slowly. It was almost entirely because our chemical engineering colleagues built amazing three-way catalysts. A three-way catalyst oxidizes hydrocarbons and reduces nitrogen oxides to preserve the electron balance. So it takes unburned fuel and turns that to CO2, takes nitrogen oxide emissions and turns those into N2 simultaneously to produce emissions that are incredibly clean. A modern three-way catalyst is probably cleaner than the air going into it. And so cities have, dramatically lower emissions. And you see that in a map. It shows up, and you see that it's about the same in all cities, and you can go city by city and be quantitative. There are lots of other ways we make maps of air quality. Here's a map of where the standard Bay Area EPA-like measurements are being made. The blue dots are where they're measuring the standard regulated pollutants, SO2, CO, NO2. Not every blue dot has all of those, but those are the typical ones. These red dots are where they do episodic measurements to get at smelly, nasty things released by the oil refineries. There's a tremendous amount of oil refining in this part of the San Francisco Bay. For the most part, we don't measure weather where we measure air quality. That's annoying. If you're just trying to make a simple plot, concentration versus temperature, means you have to go to two different databases kept by two different sets of individuals. And so most of the time what we do then is we go to the reanalysis, because the reanalysis is everywhere.
Why so many sites up north? Is that where the refineries are?
This is where the refineries are. So it's entirely driven by local communities that are disproportionately affected by the refineries. Because the refineries leak sulfur compounds and they smell. And so people are smelling the air, and people don't like to smell the air. And then the other way that we're mapping the air is there's this small company called Purple Air. Purple Air sells an optical particle counter for a couple $100. You can have that. You can either label it as inside your house or outside. It automatically gets on the network in your house and transmits to Purple Air and contributes to a map like this. I think I turned off the indoor ones, so this is just the outdoor ones in the Bay Area. And you can see this is crazy high density. It's really amazing. And every time we have a fire that makes the aerosol go high, someone else on my block buys a Purple Air. They're not really thinking that the one at their neighbor's house is really the same as at their house, but it is. No one needs, for any scientific purpose, or even for their personal health purpose, this kind of density. But we have it, and it's really interesting and extraordinary. These are the number of particles per deciliter larger than 300 nanometers. You can pull out other records. These are the particles larger than 2.5 microns. I'm not going to claim that the way they do this is sufficiently accurate, but you can just see the differences in numbers. The particles larger than 300 nanometers, the numbers here are of order 1,000, and here they're of order 10. So it just gives you a sense that what matters, we think, for health is the volume or the mass. Those are proportional to each other roughly, and so it's really these big ones that matter. So what I'm going to tell you about is our network, and we made a compromise in between those extremes. Every one of these green dots is somewhere we're making a measurement. We chose to make measurements on approximately 2 kilometer spacing. And the way we came to that guess of what's right is we look back at really old literature on Gaussian plumes. So if you go back to Seinfeld and Pandas and stuff that's derived from 1960s plume work, it says that the E-folding length scale for a plume in a city is about somewhere between 500 and 1,000 meters. And so we said if we plop down a sensor every 2 kilometers, then we're within 1 kilometer of every source in the domain. That was roughly the logic that went into the analysis. It was supported by measurements that Suzanne Paulson at UCLA made, where she drove perpendicular to a highway at times when the winds were also perpendicular to the highway, and got an E-folding length scale of about 750 meters of aerosol. And then more recently, Josh Apte, while he was at Texas or Austin, but was driving in Oakland, right in the same domain as these measurements, showed that, and same kind of E-folding length scale for black carbon and nitrogen oxides. So this spacing is about right for the kinds of things we expect in a city. If you're bored and you have your laptop out, you can go to our website and play with the observations. They're posted in near real time. You can look at the map. You can see what's happening right now. Beacon.berkeley.edu, beacon without the 2 and the CO2. I won't talk too much about it today, but I'll talk about the research part of this project today. It's coupled to a bunch of different education and outreach efforts that we have. We started this in collaboration with a children's science museum. We continued with a collaboration at the Exploratorium, a science museum that targets older children than the first museum we connected with. That was more the right age group. The under 5th grade is not really the right audience for this kind of science. And then almost all of those sensor locations I showed you are the rooftops of schools. Mostly middle and high schools, and in many of them we have a relationship with the physics teacher or the chemistry teacher or maybe an earth science teacher, someone who can bring science to the classroom. And mostly we go to those classrooms and we talk about the human path we took to becoming a scientist. That's mostly what the teachers want their students to see, is that not every scientist is the person you see on CSI. Some of us took different paths and look different than that. So let me tell you what we're measuring. We're measuring CO2. That's the core of this. That's what drives the price. That's the hardest thing. To be interesting for CO2, you need to be measuring to about a part in 400. So it drives higher precision. The only other thing that we really usually care about in the atmosphere to that higher precision is temperature. 1 degree out of 300 Kelvin matters. But We don't care about the winds to a part in 400. We don't care about all kinds of, we don't care about NO2 to a part in 400, CO, 5, 10% is good enough. For ozone, we care about a couple ppb out of 60. So really different tolerances. So CO2 is the hardest thing we do. And it drives the whole design of this project, really. But we measure CO, ozone, NO, NO2, and particles. And so roughly speaking, we can build this parts and labor, deliver to you for about $8,500. The maintenance costs are really low. It's about 10% of the hardware cost per year, and that's not, each node needs about 850. It's one in 10 has some sort of catastrophic failure, more likely. And then, and the idea is really the cost of any kind of the observing projects we do are parts and labor. And really, we're trying to drive the labor costs low so that, we can build 20 nodes for the cost of about a person year of work. And so, given that sort of balance, you're trading off. You could have more sophisticated instruments, but if they take a person year to do them, then it's not a win. So that's really how we've been thinking about this project, is how do we keep both the parts and labor costs in balance and low. And just there's an awesome team, and I'll tell you about some of these folks as we go along. Just really great people I've had a chance to work with. Okay, so just a couple photos. This is my former student Alexis Schusterman installing a node on the roof of the Exploratorium. Here she is with Jinsol Kim installing one at the other end. This is one of the few places where we chose to put nodes closer together than 2 kilometers. It's a 300-meter long building. We put one on the street side of the building and one on the bay side of the building, and those both show up inside the museum. And they look different because the one on the street is really close to the traffic, and you see variability on that one that you don't see on the bay side, except occasionally when a boat comes in and parks next to it, and then the bay side is high and the street side is low. And that's fun if you're in the museum. Should also say that we tend to think about these in plan view, but we live in an area with pretty steep topography. So my house is up here at about 400 meters. And often that's above the marine layer. And so we're looking down on the fog. More often we're right in the middle of it. But since sometimes the fog is below 400 meters, what it means is that occasionally we're seeing clean air that really has never been in contact with the surface. And that's useful for sort of checking on some of our ideas about how everything's working, but it's only accessible to these few sensors that are up at the top of the ridge. Most of the sensors are down pretty low.
Did you get snow this year? It's
We
almost
did-
like Mount Diablo altitude.
It is almost like Mount Diablo. We're not quite that high. We did not get snow, but there was enough hail when I left the house yesterday that it was slippery getting out and icy on the steps. In the 20 years I've lived in this house, we've only had snow twice, and really a dusting. Gone in a couple hours. Here's just a sense of what the CO2 looks like. This is a 3-year record. So you see the Northern Hemisphere seasonal cycle tracing the bottom. And then you see these crazy high values. Those are nighttime emissions when the atmosphere is stable. The emissions at night are probably down by 100 from during the day, but the atmosphere is probably 10,000 times more stable. So that's tricky to interpret. There's hardly any traffic, but you get extremely high excursions relative to daytime because of the stability of the atmosphere. So your eyes are drawn to this, and you tend to say, oh, that's where all the action is, but it's really not. Really, we're trying to make interpretations about both the nighttime and the daytime. So here's just to stretch out that time series and show you why it might be useful. There are measurements here. Let me see if I can pick it out. So that there's 1, 2, and here's the other one. So 4 different locations, and you can see they're often pretty much tracking together, and then there are moments where they're quite different from each other. and again, and so there's, in those moments, they're seeing different locations that, they're always seeing different locations, but the differences are more magnified in some way. And what we're really trying to do is learn how to use those differences to our advantage. So here's just showing that we're capable of calibrating. These are independent calibrations that don't involve co-located measurements made by the local EPA. So red is the local EPA and blue is us. And you can see for these 4 chemicals, we're doing okay. For CO2, we're about 1 ppm precision across the whole network. In this case, we measure it by comparing differences between nearest neighbors after calibration. So why should we be doing this? What are the advantages of a network like this? So we're making a map, and a map, you get a sense with your eye that a map tells you something than an average across the domain. We're getting about an observation every 2 square kilometers. The data are often quite locally sensitive, so many, many small footprints that we can then integrate together. There's other kinds of things that work to our advantage here. So to the extent that calibration errors are random, in the Bay Area part of the network, we have 50 sensors, so the square root of 50 in terms of calibration error might work to our advantage in thinking about a mean. So if 100 1 ppm sensors, if we could use the square root of n as a sort of a rough metric, that might mean we understand the regional bias, the regional variation to 1/10 of a ppm. I don't think we're quite that good, but sort of that's the spirit in which we can think about many measurements. And there may be, the large numbers offer the opportunity for other kinds of statistical features of the data to overwhelm bias at any one location. Okay, so that's a little background on the observations. Let me give you something of the context of CO2 emissions. California has a ton of laws related to CO2 emissions, and they're targeting getting to net zero by something like 2035 now. So that feels like far away, and then you said, okay, if we were to get to zero CO2 emissions in, let's call it 10 years because the math is easy, that would mean we need to drop, if we were going to do it linear, about 3.5% per year, 3.33% per year. And that's roughly the target we set for ourselves. Can we see a change in the CO2 emissions in the city within a year at a ratio of about 3.5%? So, and various kinds of ways. In 2006, they said 80% by 2050. In 2016, it was 40% by 2030. The most recent laws are all faster than this. What that looks like, here's what the emissions are. The emissions are, a third from transportation, another sort of a quarter from industry in the domain I showed you, mostly oil refineries, electricity generation. This is at the state level. There's almost none of that in the Bay Area domain. That's all in remote locations. Heating and cooling in buildings, other kinds of things. And then if you look at this from the point of view of a single city, this is the City of Oakland's climate action plan. The City of Oakland said if they just do nothing and let the state go about its business, in 2050 CO2 emissions would fall from 3.5 million tons to about, by 50%, to about 1 3/4. And if the city takes additional actions inside its borders, it can drop those another significant amount. So this is where we were thinking the beacon idea can come into play in terms of supporting our friends who make policy. Is can we help people who are trying to do what they think is the right thing by making policy to reduce CO2 emissions aimed at some target? Can we help them know that they really are on this lower green line and not on the pink line or not flat? And can we help them know that they're moving in the right direction for the right reason and not for some other reason? Because there's, it turns out that in the climate action plan in the city, as you might guess, there are more constituencies than people in the city. Every one of them thinks that their constituency, that their strategy is important. The folks who like email me all the time who really want my signature are the folks who want to label gasoline stations the way we label cigarettes, and think that putting a warning on every gas pump is helpful. I don't buy it. Yeah. Anyone who doesn't know that when they buy gas they're putting CO2 in the atmosphere, we're not going to reach with that warning, would be my take on it. But I could be wrong. But that's one constituency, and they might say that that's the most important thing. But what happens is that in a climate action plan, at the end of the year, the city staff has to report on every item in it. And what I would like to do is be able to show them that 3 items are really important, so they could spend most of their time reporting on the 3 important items and not on the 700 items or 7 billion items that are in the plan. So that's sort of where our science intersects with the policy. It's tricky because every city is trying to follow UN guidelines in their emissions, but the guidelines are not specific enough that people of goodwill trying to implement them would do the same thing in different locations. So there's this beautiful paper from Kevin Gurney where he got 49 cities to give them their internally generated inventory, and he compared that to a uniform inventory across the whole country. And not to say that the uniform inventory is right, just that it was a common reference standard for all of these other cities. And you can see red is, dark red is more than 100% different from the reference inventory. You can see, 2 locations, not far from here, this one and that one, or this one and that one. These people are off by 50% in Chicago, and here they're right on by this metric. And then, not very far off, they're off by more 100%. And these are all cities that are actually trying to produce an inventory using the same script.
Is there a need for a standard distance from a source? Because isn't that the main factor, how far away you are, or is that not?
So in this logic, what matters is the political boundaries of the city. Because these folks are responsible for emissions within the outline that's their political jurisdiction, and not emissions that happen even 1 foot across the line. Now, what we would like to do, of course, is stack all these adjacent and build up individual cities and communities and metropolitan areas in a way that's self-consistent. But these guys don't have any influence outside their political boundaries. They can only make change where they have authority.
How can you enforce any laws if there's such variability in the measurements? Is that the plot?
So these are not measurements, right? This is a survey instrument. There are no measurements here. This is someone gave people a form with instructions on how to fill out the form, and people filled out the form differently even though the instructions were the same, and they were all trying to do the right thing and fill out the form properly. It's because it's hard. It's just telling you that the definitions are tricky.
Can you give us an idea of what one of the questions would be?
So let me give you this one example just to say, so it turns out that where I live in the city of Oakland, in this view, we're spot on. The emissions are right, exactly the same as Kevin's inventory. But it turns out it's not for the right reasons. So when you look at it, and apologies for the fuzziness of blowing this up from the paper, blue is fuel used by vehicles that are not on the road, so construction vehicles mostly. And the 2 inventories are different by 40% in that category of emissions, even though and they happen to agree because the stationary source is often the other direction compensating. So these are all trying to tell you how much CO2 is emitted by all different processes within my political boundaries. So I think we offer a solution, an observational solution, to say not just what's a common reference standard, as Kevin Gurney did. He took one model that was the same in all cities, but an observational standard that would be independent ground truth for this. So that's what I want to tell you about. This work was done by Alex Turner. He's now a professor at the University of Washington, and came out in a paper in GRL 2 years ago. So here's what we're going to do. We're going to take a series of iterative improvements. We're going to have an initial guess inventory. So we'll have a prediction of what the CO2 emissions are and where, and that those emissions will take into account some economic statistics, some social data, whatever we can do to get our best guess at what the emissions are as an input baseline. In the language of Bayesian analysis, that's our prior. It'll depend on the weather, maybe. Then we're going to have our observations, and then we're going to do a Bayesian inverse, which is sort of an iterative improvement on our initial guess. So here's, in the counties that we span, here's roughly what we think the emissions are. It's, about, as I told you, about a third transportation, about a third industrial commercial, a little bit of electricity, and some off-road equipment. Here's what that looks like on a map. So here's the middle of the night. The emissions look like point sources mostly. You can barely see the roads. Refinery, 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 refinery. Those are the big sources. Some electricity generation over here. Then we wake up and it's rush hour and the roads jump out at you. So the big differences between the spatial patterns day and night is one example of what's going on in the domain. We built this inventory quite a while ago and used it in an experiment to ask what the power of these kind of observations would be in an Aussie framework. Yeah, as you'll all know, CO2 is not just emitted, but it's absorbed by the biosphere. So one of the things we need to do is be able to have a prior for the biosphere and a way to interpret that. In this case, what we chose to use was the solar-induced fluorescence from the Tropomi satellite as a measure of photosynthesis, and then to downscale that to the kind of spatial resolution we need, and to have a seasonally varying estimate of that. And just, important, in this view at the whole state of California, what you can see is the large forest fires made enormous changes in the photosynthesis, easily seen from space. Let's see if I can make this movie run. So here's a 1 kilometer movie run over 3 days. What you can see is that those enormous point sources can dominate your perspective on it, even though the traffic is a big deal. So that's part of the challenge here is to, so here's what we did. The first experiment we did where we really tried to put this all together was to look at a really big signal. And the big signal was the 6 weeks after the COVID shelter in place. So we look at 6 weeks before and 6 weeks after that, blocking out the transition moment. And we asked how much CO2 changed. And it was also springtime. So you may remember from the popular press at the time that there was lots of talk about ozone changing or not changing and nitrogen oxide emissions changing. Almost all of that had more to do with the weather than the COVID shutdown. The weather was an enormous confounding factor in thinking about the air pollution consequences of the COVID shutdown. It was on average over the globe warmer, and that meant there was more ozone because than there otherwise would have been. It was more ozone, that the average April was warmer compared to previous Aprils. It was tricky. CO2 is less tricky, but it's still, the weather matters. It was greener, there was more photosynthesis going on, so you can't do this without actually having a full weather model engaged in the analysis. We're doing a standard strategy for an inverse model. We're taking, in this case, the matrix H is the transformation between observations that we make and emissions at some location on the ground. And that's all we're trying to do, and then we're doing that in the context of a chemical weather model. So we have WRF, or actually HER, a high-resolution rapid refresh model, and we take back trajectories from that with a code called STILT, stochastic time-inverted Lagrangian transport. We take about 60 of those back trajectories to generate a source map from each observation, and then we solve that matrix problem of the weight with appropriate weighting. And we have a lot of observations, but it makes sense to think that some of those observations and some of the model error is extremely correlated. So if I see your hand now, let me just say a couple words. So for example, emissions on the highway at exit 16 should be almost the same as emissions on the highway at exit 17, because hardly any cars change. So we should have some covariance in space. Emissions on the highway at rush hour today should be about the same as emissions on the highway at rush hour tomorrow. So we try and build in covariances that we know belong in the answer, so we don't wander off into someplace silly.
Well, I was just thinking, and I don't know if people still do this, but for a long time it was of interest to try to tune weather model coefficients for parameterizations. You have so much information. You could constrain turbulence parameterizations.
So let's come back to that, because that's where I would love to work with you. Let's come back to that at the end. But I think that's right. I think there are ways in which letting emissions be the only things we tune is underselling the strength of the observations, and how we could let the observations both affect the emissions and the weather would be really interesting and potentially valuable. Ankur?
Are you solving for individual sector-based emissions or just the entire emissions?
We're solving for emissions at each grid cell in the domain, so a 1 kilometer emissions map. So again, here are the observations that went into this particular inversion. Here is the footprint. This white line is a contour that's about 40% of the influence. It's where the influence is most structured. We don't think we have much power outside that. One of the many tricky parts of this is that this covariance matrix gets to be unreasonably large. And so to make it possible to solve the problem, we divided that into a spatial part and a temporal part. So if we didn't do that, it would be 374 terabytes. That's hopeless. And you can see the spatial part is hard to see because the matrix is a map, and adjacent locations, when you put them into a matrix grid, don't show up nicely adjacent to each other. But the time part does. So this is, you can see the strong self-correlation at time 0, and then that decays, nearby things are correlated within a few hours, and then that repeats tomorrow and repeats a little bit the next day, decaying over time. Okay, so what did we get? So here's what we have for observations. Top is CO2, the bottom is carbon monoxide. Before the shelter in place, you see this huge peaks at morning rush hour. Those are gone, much lower. You see, interesting, the weekends are hardly any different. That's a clue. And you see in carbon monoxide, you see both the morning and the evening rush hour more strongly than you see it in the CO2. And then after the shutdown, all the signal is more muted. So what happened, this is the biggest source change, and in California, there's an amazing number of traffic counters. So in the domain map I showed you, there are 1,800 locations, 1,800 locations where someone has a counter on the highway. And most of those are counters that measure speed and weight. So we're able to distinguish cars from trucks. So this one is an approach on the Oakland side to the San Francisco Bay Bridge. You can see that before the shelter in place here in red, there was, this is 7:10 of the 5th. There were 7:10 of the 5th cars at rush hour, and then in the middle of the night, about 1:10 of the 5th. You can see that after the shelter in place, we dropped as much as by about half, with much stronger day of week dependence in the beginning than there was before that. You can hardly see the day of week over here. You see the trucks have a very strong day of week dependence. They're about 10 times less. This is 6:10 of the 4, so 10% of the vehicles are trucks. But they had a strong weekend effect before and a really strong weekend effect immediately after the shelter in place. So when we put that through the inversion, here's what we get from before. We get the average emissions were something like a little bit, somewhere between in the neighborhood of 500 tons of carbon per hour in the domain. There was a little bit of uptake by the biosphere midday, and the stationary sources, which include the industry and home heating and other things, were relatively invariant with time of day. After the shelter in place, the traffic is lower than the stationary sources almost all the time. So the orange, which is here, almost double the stationary sources, is now just at its peak touching those stationary sources. And the biosphere is a little stronger. Spring is happening. Here's that on a map. This is now every grid cell. And so you can see what happened before. We have these strong emissions on all the highways and at the point sources. Afterward, there's, you can see the green starting to emerge, so the biosphere is taking CO2 out of this air in those places, including here where we have strong signal, right next to all these big refineries. And you see that the inversion is telling us the point sources were a little bit lower, and the traffic a lot lower, especially on this highway. For carbon monoxide, we see something quite similar. The localization in space is not quite exactly the same. We can also pull this out by time of day. We get different signals at different times of day. What I'll point out is that CO2 in the morning looks like the roads. The CO doesn't so much. In the evening, they both look like the roads. We suspect, but haven't yet convinced ourselves, is that's because in the morning, people's catalysts are cold. And when your catalyst is cold, you emit really high amounts of CO, but that's before you get to the highway. And so we expect that the morning spatial pattern of carbon monoxide is really different than the afternoon one. But we haven't quite proven that to ourselves, but that's one hypothesis here. Yeah, so this just shows you what I showed you before. It's about a 25% total reduction in CO2 emissions and about 45% in the vehicle emissions. The emissions at night went almost to zero. Much, much lower emissions at night. And then just to the other chemical, we did this for carbon monoxide. So here's a 2.5 tons of CO red line. And you can see the traffic in orange here is mostly above that, and then it's mostly below that marker after. Long-term vision here, the CO2 and the CO come from the same kinds of processes, but different ones. So heavy-duty trucks emit almost no CO. They burn hotter and they burn more efficiently than cars. Heavy-duty trucks emit lots and lots of nitrogen oxides. So you might imagine if we did a simultaneous inversion that overlaid the different sorts of chemicals, that our sectoral attribution will get better. But right now we're only capable of doing them one at a time. We're still working out how to do more than one at a time. So here's just one other result. This is now 4 consecutive Aprils. So in 2018, we estimated this much CO2 emissions. 2019, a slight change. There's 2020, that was the deep COVID year. And then we're back quite a lot in 2021. Okay. So let me give you just a couple other examples of the kinds of things we've been able to learn with this network. So we'll look at two things. We'll look at speed and we'll look at fuel efficiency. So during this period, it's become more common to own a Tesla or some other electric vehicle. So you might imagine a fleet-wide average of CO2 emissions would be dropping because some of the cars emit zero on the road. They've moved, whatever emissions they're responsible are now moved to a power plant outside the city. They're not zero emission in that sense, but they are zero in the location where we're measuring. And then you might imagine that emissions are different at different speeds, and they are. They're quite a lot. So if you're in a traffic jam, the emissions you have per mile driven are almost double than if you're going at free flow speed. So we did this in a way that was not this fancy inverse model. What we noticed when looking at these measurements is if you just do a multilinear regression at every site, and you give the regression some weather parameters and the number of cars on the nearest highway, you get an incredibly strong correlation between the excess CO2 after removing the weather variables and the number of cars per unit time. And that correlation is different at every location. It's steeper near the highway and more shallow far from the highway, but it's strong. The correlation is really strong everywhere. So we spent a couple of years pondering how we could sort of do a synthesis of this that was not through using a meteorological model as the mediator. And we realized that the Gaussian plume idea that I told you sort of guided our idea of locations in the very beginning probably would work here. That we could sort of fit all of these slopes to a Gaussian plume emanating from the highways and get a rough estimate of the CO2 per unit vehicle in that way. And so that's what we did. Here's the slope, excess CO2 per unit vehicle as a function of distance from the highway. Most of the information comes at short range. We don't quite have as many measurements at short range as we would like, but it turned out to be enough. So here's 3 years. We can measure the relative change over those 3 years. What we see is roughly a 3.5% per year decrease in CO2 emissions for the average vehicle, saying that the average vehicle is more fuel efficient after 2 years by 7%. The state estimated that it would be 5%, 2.5% per year. So I'm not going to jump up and down and say the state's wrong, but we're pretty darn close to being able to measure that change over time in a way that, this is one of the directly relevant things. How fast are cars getting more fuel efficient on the road? Here's the average number for the entire fleet. Directly from observations, relatively little model. The other things that we wanted to look at were speed. So here's that same stretch of highway. Now, instead of showing you the number of cars per hour, I'm showing you the speed they were traveling in morning rush hour. And the two colors are the north and west along the bay here. It's an east-west road, but it's going north-south at this particular moment. So in the morning, one direction is typically going 20 miles an hour. It's entirely backed up. That's the to San Francisco direction. Here's the direction going the other way. It's not doing all that much better. And in the middle of the night, it's free flow, and the average vehicle is going 70, and 5 miles over the speed limit. And then we have this nice pandemic. It was great. That's when I taught my children to drive. There was nobody on the road. It was a fabulous time to be the driving instructor. I don't know about the student, but I felt much better teaching my kids to drive on the highway when there was no one else there. And there's almost no change in speed. It's almost always free flow. And there were lots of cars here. So it's not that there were no cars. Just because I think in miles per gallon, not MKS units for fuel, if you're driving here at the speed limit, the average vehicle gets something like 28 miles a gallon. If you're driving slow, it's half that per distance traveled. And if you're driving faster, there's a small decrement. So what we did was we took that inverse model and we sorted it by vehicle speed to try and get a sense of what the emissions would be. And so here's now in MKS units, grams of CO2 per vehicle kilometer traveled. This is from our observations. This is purely from the state's model of how vehicles should work in aggregate. It's unbelievably good, better than it has any right to be. There's an absolute offset of a few percent between the two estimates, but the slope, like here we have cars that are relatively using less CO2 to go a kilometer. Here we have cars that are more. So these are slow cars that are less efficient. Optimal speed's more efficient. Right on. So what we know about fuel efficiency versus vehicle speed seems to be absolutely correct. And I don't think there are lots of measurements of this, of course, on a dynamometer or for an individual car. But at the fleet scale on road, I think this is the only demonstration that we have a speed dependence, right? Okay, so I've tried to give you just a little bit of a hint of the kinds of things you can do in the sensor network. We've been trying to entrain other people to think about this. I think there are more opportunities than my group could ever take advantage of in trying to use sensor networks and think about them. There's a dozen nodes in collaboration with Will Berelson at USC in Los Angeles. We're about to send him another 10. We put 20 in Glasgow in collaboration with some colleagues at the University of Strathclyde. These 10 we sent but never quite got deployed. Meredith Hastings in Providence, some of you are collaborating with her, trying to do some modeling from Tracy's group. She's got 25. The data is live, it's in near real time, and really we'd love to share and work with you. We'd love for you to take it and go another way. We'd love for you to invest in another city. So what I can say is, we're excited about high space and time resolution observations with networks. The networks have multiple chemicals. That multiplicity of chemicals is really what makes us unique. There are lots of kinds of networks that have only the air quality gases. There are lots of networks that have the aerosol because of purple air selling them like crazy. There's almost nothing that has CO2 and the air quality and the aerosol. There's maybe a couple of cities on Earth that have those things, and none of them systematically in the same space the way Beacon is designed. So that's really where there's something interesting. We're starting to learn to make some interpretation of them in ways that are more than the sum of individual instruments, to think about daily variability in ways that teach us about processes in the domain, not just the totals, and our ability to constrain the emission trends from the individual sectors with relevant precision to policy and also rapid timing. So I didn't point out to you, but I should have. The GRL paper we wrote about the shelter-in-place CO2 emissions was published in GRL in November from observations that took place in April. So you can imagine that if we weren't trying to publish, if we were just trying to give an answer to policymakers, we could do that within a month or 3 months after making the observations. So if what you need as the mayor of your city is to be able to say, I promised you your CO2 emissions would go down, we can give you the number before you're up for election again easily. And that's not normally how scientists work and engage with the government. Normally we say, you'll give us money to do something, and sometime 2 mayors after you will give you an answer. That's not okay in this business, both because it's not an okay timescale for what we need to do to reduce CO2 to get to net zero or net negative for climate change, but it's also not okay because we need the engagement of the policy community on short timescales to get where we want to get to. So I'm just going to highlight Naomi Asimo worked on this carbon monoxide measurements, and I didn't have a chance to tell you what we're doing with ozone. That's Anna's project. Milan and Pietro are working on the aerosol, and Yishu on the NOx. And then thank you for your attention.
Thank you very much, Ron. So questions from the students first.
All right, everyone's shy. How about a faculty question that'll inspire some students?
How about a faculty question?
Matt.
I'm interested in how they measure mileage and CO2 output at different speeds. It seems like a different scenario. If you went 70 miles an hour to a certain spot, and then you went 30 to a certain spot uninterrupted, you'd get a different answer than if you tried to go 70, but you had to stop and start and average 30. And you're looking at the second scenario.
So if you go into the paper, we worried about that a lot.
Yeah.
We worried a lot about the stop and start. So yeah, that is a key part of getting to the right answer. And you're right. If you average 30 by going 15 and 45, you have different fuel efficiency than if you go 30 steady. And
I just realized I wasn't thinking about it the right way at all.
Yeah, so that's an important detail, and it's tricky. I want to come back to your earlier question. So when we do these inversions, if you look at them, we spent a lot of time and we concluded right now we have to average over a month. And the reason is that we get unphysical variation at shorter timescales. And that unphysical variation we've tied to boundary layer dynamics that just can't possibly be right. So when the atmosphere is more stable, we get crazy low emissions because the concentrations accumulate faster than otherwise. So we really do think that there, as you were hinting, that we could, at a minimum, constrain boundary layer dynamics, much, much better than we do with the weather observations we collect today by incorporating the CO2. But we haven't figured out how to do that, and I would love to talk to any of you about how you might actually affect that in real ways. I mean, one way would be to do a data assimilation where you let the CO2 observations affect the concentrations, but doing that at 1 kilometer is just hard. Just the computational resources needed are very high. So that there might be a smarter way to do it. I don't know what that might be.
So Ron, it seems like, particularly with this, the traffic change, that's where you really seem to have a good lever. What thoughts are there? I mean, how do you improve traffic flow, right? So, what's California? What's San Francisco doing about getting more high-speed rail and that kind of thing, so that traffic flow?
So my bias, I think if you look at what it's going to take us to get to net zero, we're not going to get people's cars off the road, so we've got to get them electric cars. Okay. So if I had to put my chips down, my chips are all on electric cars and carbon capture. That's, you give me $1 billion to spend, and I would put it in those 2 places. Others of you might put it other places, because watching attempts at high-speed rail and other ways to move a lot of people, I don't see them making a dent in the. Most of us drive, and we're not driving from San Francisco to LA, right? And so I had a question from an 8th grader the other day, asking me about the aviation impact on climate change, and if there was a solution. And I said, well, biofuels are probably the solution for aviation. And that would be what I would pick. You could also say carbon capture, free air capture, but that's the place where you might imagine that high-speed rail could compete with aircraft. But it's just, I don't see it. I think the more likely scenario is people will fly and take the train. So Ankur, and then Gil, and then Tim.
Thanks. This is really cool technology development. I just wanted to ask you more about one of the challenges we've always had with regional tracer transport inversions is that they're often overwhelmed by the inflow signal. It seems like you have an advantage here, partly of where San Francisco is located in terms of what your upstream conditions are. But I'm curious to what extent your inversions are sensitive and what you're using for your boundary condition measurements.
So we're actually letting the boundary condition float and inverting for it.
Okay.
I think my sense is that the information redundancy in the 50 observations is enough to specify the inflow boundary condition, but it is a good question, and we're doing it at the 4 different north, south, east, west edges. Right. So we're allowing them all to float, but that's tricky. Gil.
I want to follow up on Brad's question. Are there specific policy changes that come out of your specific measurements that are occurring now?
So there is no. So I was telling some folks, I'm really a curiosity-driven scientist, so we're trying to understand how the world works. I happen to be curious in this place that's policy relevant. It's awkward for me. It's not my thing. So I believe that we should be able to learn to communicate with cities in a way that says your policy about electrification of trucks near the port that you're doing for environmental justice purposes is working or not working. And here's why it's working and not working, because we have observations of what's happening in the atmosphere. That's a piece of the, that's a step past the atmospheric science into the social science where I'm not as good. But I know I need to get better. But that's the kind of thing where, if the city says, we're gonna, if you want to electrify the vehicle fleet in your city, one of the things it depends on is charging. And it turns out, I learned from being on a qualifying exam in engineering, in the transportation engineering department, the grid is cleaner during the day than at night. So if we go home and we charge our electric cars at night, it's not as environmentally friendly as if we charge them during the day when there's more solar and more wind. And I didn't know that, and I'm plugged in until I sat on this qualifying exam. So probably the number of people who know it is really small, or maybe I'm just out of it. So you could have a policy then to say we should have more charging where people shop and where they work, and that's where we would intersect and help.
Maybe just follow up, like, does your data show, for example, if you spread out the times that people start work, if you could spread out the rush hours, would that actually make an impact?
So our data does show, what we already knew, that if you drive in a traffic jam, you have more emissions than otherwise. And so that goes to what Brad said. If you can reduce congestion and move the same number of people, you would have less emissions per motion of people to and from their homes and work. But we've done that the other way. Now we're letting huge numbers of people work from home 2 days a week. That also reduces congestion, and reduces maybe a little bit the number of miles traveled if they don't go shopping too much, or depending on how many Amazon trucks come to their house. This would be my case. Tim.
I had a question about sensor placement. So you said you set them up at a kilometer scale because you capture an e-fold off of any source in the city. But in a city like this, we know where most of the sources are. So if you were to make this again, would you prioritize setting the sensors closer to the larger sources to capture the shape of the day? Or would you still do it this way as we start to think about setting these networks in all these other cities around the world?
Yeah, so I think if there's lots of different science questions you might want to answer. And so I would still do it this way because it's really generic and it allows you to go after other things. Some of the folks who are driving, some of the interesting things they found driving cities, so they put really good sensors in a Google car and they just map the city. And that's sort of the competing alternative to Beacon that I think is most effective right now. They've found sources that aren't in the inventory, sometimes big ones. And so that would be the reason to just be generic. But they're a good, the other thing is that if we, for example, if we learn to do methane, and methane emissions are episodic, and so they're not just rush hour and point sources we already know about, you might say that we should, if you have episodic emissions or you don't know how the emissions work, you want the uniform grid. So I want this for home heating. I want it because I really don't know whether I believe the story that most of the automobile emissions are when catalysts are cold first thing in the morning. So there are reasons I want to be more generic and more uniformly spaced. They're mostly because I don't know that I believe the emission inventory to start with.
Okay, well, thank you very much.
Thank you again.
Good
It was really
questions.
fun.